One last question that came from our Barrons practice. We have a bungee jumper who has reached a point where the cord is 100 feet long and has a radius of half an inch, and it is stretching. She's still 80 feet above the ground and is falling now at 40 feet per second. We want to assume that the cord has a cylinder with a volume remaining constant as it stretches, and we want to know at what rate is the radius changing at this instant when the radius is 1/2 of an inch. All right, so this is a related rate question. So let's start with our equation first of all. So the volume of a cylinder is pi r squared times the height. There's the volume of a cylinder. So this is a related rate question. We want to find the rate at which the radius is changing. So we need some implicit differentiation. So I'm going to find the derivative of all of this with respect to time. Okay? I'm just going to make this a little bit smaller. All right, so we're going to take the derivative of v with respect to time. And over on the right-hand side, we have product rule, right? We have the first and we have the second. So we're going to take the derivative of the first, and remember this is implicit differentiation, times the second, plus the first times the derivative of the second. The derivative of h is 1 dh dt. So there is our implicit differentiation. So from here, we're just going to substitute in all of our variables. So the volume is not changing. It does tell us in the question that the volume remains constant. So there is no change in volume. We are at this point where the radius is 1/2 of an inch, and we want to find dr dt. And the height is this part right here. So there's basically the height of our cylinder. So that is 100 feet. But before I go on, I just want to make sure that our units agree. We actually can't use 100 feet. So this is probably the only thing we really got to consider here. And you may want to write this down on a piece of paper so you have it on the exam. 1 foot is 12 inches. So 1 foot is 12 inches. So if this is 100 feet long, that is 1,200 inches. Now we're going to have to do that really because this is in inches. We need this in inches. We need all of our units to agree with each other. Okay, let's keep going. We got pi, we have r squared, so 1/2 an inch squared, and dh dt. We're told that we are falling at a rate of 40 feet per second. Well, once again, using this conversion, 40 feet would be 480 inches per second. So there is our equation, and now we're just going to solve that equation. So I'm going to go here, and we're going to try and solve for dr dt. So we need all of this first part over here. We're going to punch that into my calculator, and then I'm going to move it to the other side. So doing all of that, I had 376, but I'm going to move that to the other side and get negative 376.991. I'm going to solve all of this. These two cancel each other out, so we really have 1200 pi and then dr dt. So let's divide off 1200 pi, and when we're all done, dr dt, the rate at which the radius is changing, becomes negative 0.1. That will be inches per second. Now, inches per second, sorry. Okay, let's take a look at the second part of this question. All right, in part B, we are looking at the bungee jumper, and we want to figure out the rate of change of this angle of elevation. So we're looking at this angle in here as the bungee jumper falls. All right, so again, it's a related rate, but now we're looking for an angle. So I need something that relates this angle to my sides that were given. So that is tan theta will be opposite over adjacent. So let's call that, let's call the opposite here the height that we're above the ground. So I'm going to call that h. And the adjacent is 60. Now the nice thing here is the adjacent is never going to change. It is always going to be 60. So I'm just going to put 60 into my equation. Let's take the derivative. We need the derivative with respect to time. So we're going to do the derivative with respect to time, implicit differentiation. So the derivative of tangent, remember we had this little box here, negative, there's a negative, cosecant, cosecant. We had this little hint for ourselves. But again, now you're going to have those right beside you. I sent out something yesterday. So we're going to say secant squared theta d theta, oops, almost forgot this, d theta dt is equal to, on the right hand side, we have the derivative of the top times the bottom minus the top times the derivative of the bottom. Well, the derivative of the bottom is 0, so that's all going to be gone, all over the bottom squared. So this is nice too because that is going to disappear. Let's go to the next step. I now have secant squared theta d theta dt, and we need the rate of change. Well, we actually had it in the previous question. The rate of change was 40 feet per second. So this height here is actually decreasing 40 feet every second. Now, in the previous question, we had to convert inches and feet. We really don't here because the 60 that we have in our equation is already in feet. So we're going to say minus 40 over 60. There's my dh dt over the 60. Now we really just want to rearrange this to solve for d theta. So I'm going to slide this up. Okay, let's find d theta dt. So let's keep going. I'm going to rewrite my secant. So this becomes really 1 over cosine squared theta, d theta dt. So it's really just a lot of algebra here. I'm going to simplify this as just negative 6 over 4 over 6. Just kind of cancel that out. I could have said 2/3 too, but we're okay. Let's multiply then by cosine squared theta. So there's our formula for d theta dt. Problem is we don't know what theta is. Well, let's go ahead back to the original square triangle that we have here, and let's just figure out what theta is. Tan theta was opposite over adjacent. So if I go into my calculator and I do tan inverse of opposite over adjacent, I can figure out what theta is. Now, when we're working here, make sure my calculator is in radians. I'm in radian measure for all my trig stuff. So I'm going to go inverse tan of 80 divided by 60, and my angle, theta, is 0.927. So I have negative 4 over 6 cosine squared 0.927. So that's our setup. Let's just slide this up one more time. And finally then, d theta dt. Let's just punch all of this in. I'm going to take cosine of the answer I just had and square that. And then I'm going to multiply it by negative 2/3. So I'm going to multiply that answer by negative 4 over 6 or negative 2 over 3. And I have negative 0.24. This will be in radians per second. And that's that solution there. So there could be some implicit differentiation tomorrow, so be prepared.